Yeah, hi everyone. Welcome to Prop Stats 6, I guess. Prop Stats 6. So this is in this class we'll mostly look at um, probability distributions, or we'll begin probability distributions, um, and we'll only uh, we'll mostly be going over the theory. The practical implementation we'll look at it in the next class. So this is the agenda. We'll look at the basic goal of probability and statistics, like what are we even doing with learning these concepts. Then types of quantifiers, like the whole objective is quantifying uncertainty. So what ways are there of doing that? Then some definitions. Then we'll look into the second flow, which is the frequentist flow, and we'll look at the distribution functions, which is basically the way we calculate this uncertainty. Uh, and this is the dataset. I'll put this in the description. So let's begin with the first topic, which is basically like what is the goal of probability and statistics? Like what can we even do with the prop stats in the real world? So the objective is basically quantifying uncertainty. Like we want to measure uncertainty or randomness. We have already done this in one way. In the second class, if you watch the second class, which is prop stats 2, we have gone over the concept of Bayesian, what is that? The Bayes rule, right? We have conditional probability and Bayes rule. So the fun, rather, let me think a little bit. Okay, I guess yeah, that's the fundamental idea anyway. So we will look now how can we how can we quantify this uncertainty? We do it using these two methods, which is or these two ways. Like you can think of them as different ways. One is the Bayesian way, which we already saw in the second class, which is the Bayes rule, conditional probability, etc. And the other is the frequentist approach, which is what we'll be looking at today. So that in both these ways, we are trying to quantify the uncertainty in different things. Rather, there are different uncertainties we are quantifying. In the Bayesian way, the uncertainty is that we are trying to find a value for the parameter itself. Now, what is a parameter? I guess I should define. I should set the definitions first. So, let's say I have a call center, right? So the call center is the system. Rather, I guess the much more easier one would be, let's say we have like a street. You have a cross section and there's a lot of traffic there, and you have traffic lights, and you have the cars, you have the vehicles, right? People are crossing. So this entire thing is a system. This is the real world is the system, and what we are trying to do with the system is we are trying to model the system. Now, what is modeling? So modeling is like the map of the traffic of the traffic signal, basically. So it's like Google Maps. So Google Maps is like a abstract representation of the real world, right? It is showing you what is happening in the real world. Something like You have the artificial roads on the map, right, on the UI. You have the signals, you have the estimated time. These are all part of Google Maps, and it is representing the real world. So that is your model. The system is the real world. The model is your map. It's the representation of the real world. And the model contains different, it's like a composition of different things, like the something called parameters, which is what we will actually find in, which is kind of the objective of, or rather, yeah, it's one of the objectives of computing uncertainty. You have parameters, and then once we spin this, we will get the data, or rather the data it generates is the random variable that, or the uncertainty that we are trying to find out. So when we say we are trying to quantify uncertainty, it is the random variable, or rather the data that the model spits. That is the that's what we are trying to find out. So if I take another example, let's say, or rather, let me just finish the Google Maps example itself. So in Google Maps, you have just a second. So in the maps, you have like different lanes, right? Different roads going to different places. You have traffic lights. You have the vehicles themselves, right? Maybe some accident happened, so there are some alerts. So the parameters here, so the maps is the model. So then what are the parameters? Like if suppose this is a machine, assume the maps is a machine, then what controls this machine? Like every machine has some set of switches, some knobs, right? If you change the knobs, the entire, it's like a radio. Like if you change the radio knob, the song changes, the sound changes, the tune changes, whatever. Like the data it generates changes, right? So same way in this machine that is Google Maps, the knobs can be something like different algorithms. Like if a traffic light changes, at what frequency it changes, at what time it changes, that can be one knob, because based on the traffic light, your entire vehicle data will change, right? Like if the traffic signal says red, then all the data will stop there, which is all the vehicles will stop there. If it says green, then if it gives a green signal in a different in a different lane, then the vehicles will move in a different direction, right? So the entire data will change. So what is the data here? The data is something like your estimated arrival time, right? Yeah, something like ETA, right? Like how long will it take to reach a particular destination, or something like that. So to give you another example, if we take the call center, let's say I'm running a call center. The entire call center, the real world, brick and mortars, the people, the machines, everything, the call center is my system, right? And the model for the call center would be my set of algorithms, like or the algorithm which can be my formula or whatever. Although the model, the definition for a model in stats and in machine learning, there is a slight variation, but just for now, simplicity's sake, just think of it as formula or an algorithm. So what was I saying? Yeah, so so the model in this case can be something that maps the behavior of my call center, right? It's like a map. Again, we saw the real Google Maps example, and in this case, the model will be my map, which kind of maps the behavior of this system. So, so consider this as a machine, and the knobs for this machine. So, like if you tweak these knobs, right, the data changes. So the knobs can be something like I want to know, or rather, average phone calls per hour. That can be one knob, right? Average calls per hour, or average calls in 8 hours, etc., etc. There can be multiple knobs. It's not just limited to one parameter. The knobs or the parameters can be many. And the data that it generates is something like number of calls per hour, like the fixed quantity of calls. So so this is our generated data. The model is responsible. Based on the model, you will see different types of or the data gets changed based on the way you tweak the model. So to give you formal definitions, the system is like the real world, and the model is like the map of the real world, where the model, to make it formal, the model in stats is something like probability distributions. To put it simply, it's probability distributions plus some more, plus parameters, plus the outcomes or the data space, something like that. So it's a combination of set of, it can be single or many set of probability distributions. In machine learning, you can say it's slightly different. It's like a large parameter. It's a large function, you can say, large function that kind of maps in. The outputs and inputs are mapped. But yeah, you can ignore this definition for now. Just think of the probability, the stats definition, which is basically it's a model is a set of probability distributions. Okay, I guess I forgot to write parameters. A parameter is basically a true value or a property of the system. Let me not say it is, I mean, true value is there, but it's a property of the system. Okay. It's not bad. 1 second. It's a property of the system. You can also call it as the true value of the system. So it is a fixed unknown, it's a true fixed unknown value, and the parameter is the thing we are trying to find in all the cases. Although it's one of the things, let's put it that way. It's not the only thing. It's one of the main things that we are trying to find out in all the cases, in every uncertainty that we are trying to quantify. So uh, the definition I gave just now, so something like true fixed value, what else did I say? It's a true fixed value that is unknown. What does it mean? Like, what does true mean? What does fixed mean? And what does unknown mean in this case? So let's say I have we can take the call center example itself. So I have my call center, right? This is my call center, and and let's say this call center gets not gets. So if we look at the call center, nobody can say that this call center will only get, like, say 10 calls per hour. Nobody can say this, right? Because there are so many factors involved, like so many variables involved, that many people can call at any time, and at any, like, there could be, like, you could get 3 people calling per hour, or you could get maybe even 100 calls per hour. There is no way we can know every single variable that is present in the real world, right? So what is this true here? So true means, in some idealized scenario, like suppose there is a supercomputer that actually knows every possible thing that's happening in the world, right? And ideally, when it knows everything about the world, it will know exactly how many calls can come per hour, ideally. I guess this can be slightly complicated. Let me take a simple example. So let's say there is a box of chocolates, right? And this box has exactly 10 of them, 10 chocolates. But I am an external person, and I'm trying to count all the chocolates in this one. I don't know how many there are. But there is a true value called 10 here, because this system only contains 10 chocolates, right? So that is the true value here, which means when you know about the entire population, then you can find out the exact parameter. So this is a bit hard to explain. So so in this case, like, that's what true means, true and fixed. So this is the real value of the system. But when I'm counting, if I'm like, if I don't, let's say I don't know counting, and I'm like just randomly guessing the values, I can guess it as maybe 3, or maybe I can take a random guess of 9 or something like that. But this system has a true value, which is basically 10, right? And from this I can make any sort of conclusion, because I know the entire population of this. You can only when you don't know the entire population, that is when you will not know the true value of a parameter, which is basically what it is in the real world. You cannot know everything about the real world, so it'll always be unknown, and you can never reach the true value unless you are in some idealized scenario, idealized condition like this, right? So basically that's what parameter means. It's a knob. It's a property of the system. It's a property of the system that when tweaked, it will change the entire data it generates. Coming back to the Bayesian and frequentist ways, I guess, what were we talking there? Okay. Anyway, so these two ways are basically trying to quantify different different values. However, they are trying to quantify uncertainty. The uncertainties are different in Bayesian. So if I take the Bayesian, way, what it does is the uncertainty here is the parameter itself. We are trying to find the value of the parameter itself, which is the knob. The property of, we are trying to find the value of the property of this of a larger machine, the system. And here the things that are fixed are, the data is fixed. So what the Bayesian way does is, we already have the data, and we are trying to see if we can generate if a model fits this data. So from data to model, right? While in frequentist approach, we are going the other way around. Here model is fixed, and we are trying to see if the we are trying to not generate the data, but we are trying to see if the data how do I put it? Let's just say if the data fits the model for now. Let me think of better wording. But in frequentist way, the uncertainty here is the data. It is the data is the random variable in this case, while in the Bayesian approach, the parameter is the random variable, and the fixed component is the model. And when we say fixed, it doesn't mean we know it. It's just in both the cases, we are still trying to find the model, the true value, but we kind of have an estimation of the model. Just think of it that way for now. I think when we solve the problem, this will get more clear. So so that is the basically that's the approach, or rather that's the difference basically between. Oops, where is undo? Give me a moment. Oh yeah, there it is. Okay. Yeah, so this is the high level difference of both the approaches. Now let's look at the frequentist flow in detail. Here we are trying to, we already have a parameter value. Sorry, did I say model? The parameter is fixed. So not the model. You can say model as well, but the thing here that is fixed is the parameter. So we are trying to see how the data matches the model. So the very first thing we will do is define the random variable. So if you see, we are here right now. The first step in frequentist approach is define RV. We define the random variable. Let's take the example of the same call center itself. The random variable here can be number of So it can be number of calls per hour. I want to know how many number of calls my data center will receive every hour. So that's the unknown, that's the uncertainty that we are trying to find. Now, we already saw in the previous class, I just gave a brief overview. Random variable can be any situation or an instance or an experiment where the outcome cannot be predicted, right? That's the whole point. We want to quantify this unpredictable situation so that we can make better decisions. And this random variable can be a discrete value or a continuous value, right? A discrete value basically is countable. You know what the next number can be. You can actually count it. It's a countable infinity. While continuous random variable, it's uncountable. It's like you will not be able to know the next number. So if I have 1.1, what is the next number of 1.1? It's 1.111. Is it 1.112? You don't know. So there is an infinity between every two numbers. So it's infinites. And so for example, for a discrete random variable can be a simple one will be the outcomes of your dice roll, right? Outcomes of a dice roll. If it's a 6-sided die, it can only be 1 to 6. It cannot be 0, it cannot be 7. And same with coin toss, it can be heads or tails, nothing else, right? If it's a 2-sided fair coin. To give a much more real world example for discrete random variable, I would say anything related to categories, you can think of them as discrete, although you can have something like I guess dice roll and coin toss are decent enough. I'll think of some later on. I'm not really getting them now, but there's plenty of continuous examples. So like for continuous, you can think of heights, right? If we measure heights, right? Some people can be 6 feet. You cannot have exactly 6 feet, although there is such a quantity. You can have 6'1", 6'2". There's 6.11. There's 6.12111. So you have many values, right? It's not perfect integers. Same with weights. Same with temperature. Same with lot of real world things which are basically continuous. So once we define the random variable, then what we will do is we will build a theoretical model. The theoretical model is basically your set of distributions. The distributions can be build theoretical model. So the distributions, you can actually create your custom ones, but we will only look at something that's already predefined. So you have predefined distributions like Bernoulli, then binomial, then you have exponential, there's geometric, there's Poisson, Poisson, I don't know how you pronounce it. I think it's Poisson, but um, like there are many other. Each of these distributions um, are like meant for specific scenarios. If there is a yes or no scenario, then you use Bernoulli. Then you use a particular range for Poisson distributions. Again, maybe I'm mixing some things up, but yeah, basically every scenario, every distribution tackles particular scenarios. So we apply a single one or a bunch of these combined along with the params and some data will constitute your model. That's how you build the model. Once the model is built, then you perform calculations, which is basically calculate theoretical predictions. So coming back to our example, like if we have a call center, once we defined the random variable, which is number of calls per hour, this is the uncertainty that we want to quantify, then in the second step we can ask questions like how many so based on this we can select a predefined model. So in the third step we can ask questions like how many number of calls will I get in this particular hour, or how many calls will I get, or rather will I have 20 or less than 20 calls in the next 1 hour, something like that. You can ask interesting questions like this and perform calculations, and based on these calculations you take a decision on whether to move forward or scrap the idea or something like that. So you can say, and this is where the concept of distribution functions comes. The calculation part is where the distribution functions come. So coming to the distribution functions, you have something like PDF. So what PDF is, the full form is probability density function. So what this is saying is get me the probability of the random variable within a certain range. So you have a range. So this is represented as something like P of, let's say I want within a particular range. So let's say 60 calls to 70 calls. So what is the probability that I will get 60 to 70 calls in the next hour? Right? So this is, you can actually visualize PDFs using a histogram or even a KD, kernel density plot, right? That is one type of question you can ask. The other one is PMF, which is basically called probability mass function. And by the way, PDF is for continuous random variables. Continuous random variable. PMF is for discrete random variable. We saw, right? Continuous means it will have decimals. Discrete is like integer stuff. So PMF is like saying get probabilities of the exact value. So something like, what is the probability that I will get exactly 20 calls in the next hour, right? So that is something like p equal to 20. That is written something like this, p equal to 20. Now the third, and you can visualize PMFs using bar plot for visualization. And the third category, or the third calculation or distribution function is something like CDF. CDF is basically cumulative distribution function, and this is for both discrete and continuous random variables. So what CDF says is, get me the probabilities up to a particular value. So the notation will be something like P of, this will be X, the random variable is X, right? P of X less than or equal to, let's say, 20, up to a particular value. So this is cumulative. Wait, is it cumulative distribution? Yeah, so basically what we are doing here is, so let me take a smaller value, so let's say less than or equal to 4. So if I say less than or equal to 4, we are computing all the values from P of X equal to 1, P of X equal to 2 plus P of X equal to 3 and P of X equal to 4. So we are we are taking the cumulative value until the particular point, which is here. In this case, it's 4. And you can visualize this using a line plot, which can get a little complicated. We can also use a ready-made one in Cbon, which is sns.ecdf plot. This will allow us to visualize this thing pretty easily. Let's see. I hope that was clear. And we also, in the calculation part, we also do something called expectations, which is basically the expected value, which is nothing but your weighted average. So based on this expected value, you make your decisions actually. So this will cover in the next class about how we'll calculate weighted average, and there's a particular formula as well for this one. And once, let's say you decide to proceed, right? You have, taking the example of the call center, you have, you understood that, okay, I'm getting 20 calls per hour. And so, or rather, you have estimated that you will be getting 20 calls. You might be getting 20 calls per hour, and you did your calculations. And now, what you want to do is you want to validate this, or rather, you want to test this empirically. So, empirical validation is nothing but you are going to test your theory with the real-world observations. So theoretically, based on the model, you generated some data and you came to the conclusion that you might be getting 20 calls in an hour in the real world. Now you want to proceed with the testing. So you will collect the data. You will see in an hour how many calls you are actually getting in the real world. And you will compare it with the theoretical data. So the real world observations you will compare with theoretical data and say, uh, if your if your theory said 20 calls, but practically you only got empirically you only got maybe 16. You only got 16 or 15 calls. So there is a gap of 5, right? Which depending on what is the tolerance for error, all that stuff is there. So there is something called plus or minus 2 standard errors. It is okay as long as it's that, but if it's more than that, that means if the gap is more, in this case I think the gap is more, we can calculate based on standard error, but we'll see that later on. Let's say the gap is more. What it tells you is that either your model could be wrong model, or maybe incorrect data collection process. There's a problem with data collection, or it could be there could be some other issue which you have to do a root cause analysis for this and figure out why your model is not matching the reality. So this is just like if suppose you are using Google Maps and the roads and it maybe it didn't give you the correct directions, you'll probably crash into something else, or you'll probably end up in a different place, right? So you want your map to be as close to the original reality as much as possible, so that you not only, so why do we need to do this empirical validation? So you might ask, like, so this is one of the reasons. So that in real world scenarios, like let's say I'm in the call center example, the model will help me predict my capacity, right? I can estimate the capacity for the next day or the next 100 days, whatever it is, and based on that I can make hiring decisions as well. So if the calls are wrong, and suppose my theory is saying 20, so I'll probably hire way more than necessary, right? So that puts me in loss. So this is the reason why we do this validation. It's basically testing. Like you want to know if the product you created, it's working properly or not. So you will do some real world testing. So this is something like that procedure. And in this empirical validation step, you will see that there are, you can do many things. There's something called hypothesis testing as well, and which has like different types of tests for different scenarios, like t-test, chi-square test, ANOVA. There are different things which we will see in the upcoming section based on this, which is basically called hypothesis testing. Yeah, and once you get you find the root cause, you see everything, then you will go for the final step, which is model refinement. So in this step, you will see that should I change it to a different model? So let's say maybe you chose in the list of models here, maybe you chose some binomial, maybe. So instead of binomial, should we switch to Poisson distribution or something? You will ask these kind of questions to tweak the model and then proceed, and then again start from the first step. So this is the entire process of, this is the frequentist flow of quantifying uncertainty. You are trying to define uncertainty. Now this is the theory part. We'll see this probability distribution functions in code a little bit, and we'll call it a day for this class. So this is the dataset I'll be using. So I downloaded the weight heights. Will be performing or will be calculating this PDF, CDF, PMF values for heights in this dataset. So this is the weight height CSV. So again, we'll do the usual. I believe I already have the things, but yeah, I guess let me follow this pip install numpy pandas matplot c1. Yeah, I'm pretty sure I already have this. Then import numpy as np, import pandas as pd, import matplot as plt, and import c1 as SNS. So I have my imports. Now we will load the data frame. So df equal to, or rather we'll load the heights data. So pd dot read csv. It is this one. Let's look at the top rows. So this is our data. Again, we'll only be looking at the height data here. So df heights. These are our heights. Now let's check the max ones. The max height is 78 and the min is 54, and the total number of values, we have 10,000 records. Now let's see. Okay, we'll visualize the values. The actual code part, I think it's better if I tell it when the context is right. So we'll just visualize the graphs and make some conclusions. Let's see. So for P, let's say PMF. Let's do for PMF first. So for PMF, the graph will be a bar plot. We will see something like, okay, so now heights is continuous variable, right? So, and bar plot is not ideal for continuous data. So what we will do is we'll cut this data, or we'll bin this data into particular intervals, and then show a bar plot for this. So something like we can do df height dot cut. Let's see the. Okay, I think it's pd dot cut. Yeah, pd dot cut. We will say cut the x is the array, which is the heights part, and then the bins will be, we'll cut this heights data into interval of into three like three element intervals. So bins will say something like np dot a range. We will set the, we'll call this max, we'll call this min, and what we will do is we'll start from min to max with the step size 3. We'll pass the bins here. Let's call this TF. Let's see what it gives. So we have our heights. The bins are ready here. Okay, let's convert them to ints. I guess we don't want that range. Okay. No, not this one. Dot as type. No. Key error. Is it type? No. Okay. Oh, that's okay, that's the problem. We already assigned df here. Fine. Let's call this dfh, and as type should work. Okay, there it is. Now, okay, but it did not convert to ints. I guess we have to assign it. We'll convert it here itself. So height, so max 78, min 54, and we got the ints. Now okay, so we will actually create a separate column called bins for this, and then look at the head. So we have our bins and the respective heights in those bins. So all we have to do now is plot the bar plot, sns.bar plot. So the data will be df x would be x will be our bins okay, since we already gave df, it will be bins, and y will be our height. There you go. So these are the bins and their respective quantity of heights. Yeah, so this is but wait a second, I don't think this is, no, this is not, okay, this is not PMF. 1 second. Actually, we have to, yeah, we have to take the count of these bins. So we have to do something like df the bin values, which is basically bins dot value counts, and we'll do a normalize because we want percentages. We see this will give us the if we take normalize out, this will give us how many values are there in each of the bins, right? So this will tell us 26% of values are there in the range of 63 to 66, right? Now we'll do sort index. So this will give us the sorted values. Now we'll create a separate data frame for this. Let's call it PMF. Now we have to use PMF here, and in this case X would be PMF dot index, and Y would be our proportion. We look at this, data source must be data frame or mapping, not class. Oh, okay, reset index. So now we have a data frame. So here call this bins. Data source must be data frame or PMFCs. Series. Okay. Okay, now it's a data frame. Now, there you go. So that is how you visualize PMF. So from this we can clearly see that maximum heights are within this range, 63 to 66, right? And yeah, so we can draw some other conclusions, but basically that's how you see, that's how you visualize PMF. Now let's go to PDF. So PMF is for discrete random variables, and PMF is for discrete random variables, and PDF is for continuous, right? So for continuous, we will simply use histogram or KD plot. So we'll simply do SNS dot histplot, and if I'm not wrong, I can drop it directly. The data, if so something like, I can drop the actual data itself. So df, I will say heights. So that will give my histplot, right? And I can do something similar with KDE as well. KDE plot. Both are used to visualize continuous data. So again, histogram, the thing is, you see these are intervals, and in each interval you will see the number of values that are present within that interval. So you can see here in the range, I think 65 to 67-ish, something like that, we have around 850 or something like that values within that interval. Now, one thing to note, while there's people say that KD is just smoothened histogram, which is true shape-wise, but it does not mean you can do a one-to-one mapping for this. So just because you see here, this is mapping to 800, doesn't mean you can call the same. It's generally not recommended to make a one-to-one mapping there, even if it is, because it's not using the histogram data, it's using the actual raw data itself directly, and it has a different calculation, or rather it uses a different formula to compute the values on the graph. So the way you read KD is something like the heights, the area under this curve. If you see, if you want to know like the number of heights between, rather the number of people between heights 60 to 70, you just have to compute area under this curve. What else? You can also say like half the values or half the population is less than height 65 or something like that. The median height is around 66 or 67, something like that. And we will look at this in detail in the next class or something like that, or maybe in the next class. The final one to finish this, it is CDF. It takes both discrete and continuous. So this one we will use a special plot called eCDF, which is particularly meant for this CDF plotting. So as you can see here, this has a stepped S curve. This we can use either a line. We can use line plot as well, but that gets has slight complication. And this one we can directly drop in the dataset, and it will do the heavy lifting internally. So if you see here, what this is saying is you can compared to histogram, you can tell things like actually you cannot say in histogram that a certain section of population is less than 65, height 65. That actually you can say it in here. So because these are proportions, you can say the half of the population is less than 65 height less than 65. And if you see here, these are the percentages. So this is 20%, 40%, 60%, 80%, and 100%. So you can say 80% of the people are of height at height 70 fall under the, or rather 80% of people fall under less than or equal to 70. So that's what CDF is, right? Up to a particular value, we are checking up to a particular value. So you see here, almost 100% of the people are less than 75. That's the height. So that's how you read the data. You can get the median and all that stuff. And basically that is it for this class, and I hope that was clear. I'll explain things in more detail in the next class, but yeah, that's it for this one, and yeah, I'll see you in the next video.